Welcome to this seventh and final session on atomic structure. We're going to be looking at some extension material here about the mass spectrometer, and we can use this to detect the masses of atoms as well as molecules. So on the right here we've got a schematic of a mass spectrometer, and the thing I really want to focus on to begin with are the four basic stages that we can talk about in mass spectrometry. So certainly for this type of analyzer anyway, which is a magnetic instrument. And so the first stage of our mass spectrometry is going to be ionization. Actually, it's got to be ions that we're analysing rather than neutral atoms or molecules. So we need to convert the atoms or molecules into ions, and then the sort of classic way of doing this is with a so-called electron gun. So what you might do is excite electrons off a hot cathode, accelerate them towards an anode, and that electron beam, those electrons, high energy electrons, when they strike an atom or molecule, they'll typically knock an electron out. And that's depicted here in this equation. M, our molecule, plus an electron from the electron gun, knocks out an electron, creating an M plus cation, and then two electrons coming off. Once we've created the ions, our next job is to accelerate them. So once they're accelerated, that will then be an electric current. And it's really the electric current that we're going to be detecting with the spectrometer. So what we're trying to do is we're trying to form 1+ ions, and we can accelerate them with a negative potential, so minus V volts. So that will accelerate those ions, and that will ultimately give them kinetic energy. Now once we've got that ion beam with its specific kinetic energy, that's an electric current. And when we send that electric current into a magnetic field, we're going to cause a deflection. This is Fleming's left-hand rule with the Lorentz force. And so what we've got in the picture here, we've actually got the magnetic field is going to be perpendicular to the page. So with a perpendicular magnetic field, the electric current going vertically upwards, it's going to experience a deflecting force to the right. And so we can see our beam curve around to the right there. So this is the deflection. And so ultimately the force is going to deflect the beam, and the amount of deflection we're going to see is going to depend on the mass of the particles. So the heavier the particles, the less they'll be deflected by the force. And so having deflected the particles around into this curved path, what we finally have to do is to detect the ions. And so of course, because it's a current, they are detected using these so-called Faraday collectors, where the ion current passes into these sort of metallic cups, and because we're working under high vacuum in these spectrometers, these ions, when they arrive, they effectively create a very small electric current at the Faraday collector, and this tiny current is amplified by those amplifiers that are shown up to a level where they can be recorded by an instrument. Now, looking at it in a bit more detail, we can actually write some equations to represent what's going on in the spectrometer. So we'll have a mass M for our molecular ions. They'll have an electric charge Z following the ionization, and they're going to be accelerated to a speed V by the negative potential, minus V. And so this potential, a voltage, this is defined as joules per coulomb, energy per unit charge. So if we multiply the charge of the ions by the potential V, that will actually give us a value for the energy, and this energy is going to be manifest as kinetic energy. And this is why in the equation we've got Z times V, the charge times this voltage, it's going to be equal to half mv squared, our formula for the kinetic energy. So what we can do is we can make V, the speed, the subject of this equation, giving us that expression there. So having accelerated our ions up to a particular speed, we then send them into the magnetic field, and so they're going to experience this force, the Lorentz force, and that force will bend the particle beam around, and because the particle beam is always perpendicular to the magnetic field, it will always experience a force perpendicular to its direction of motion, which is going to force it into a circular path. And so that circular path is going to have a characteristic radius. And so we can describe it as a centripetal force mv squared over r, and this is going to depend upon the strength of the magnetic field. It's going to depend upon the charge on the ions and how fast they're going. This is relating to the magnetic field line cutting. So this centripetal force, mv squared over r, we can equate to bzv, the magnetic field strength times the charge times the speed of the ions. So again, we can rearrange this equation, and that will give us a different expression for the speed of the ions. And of course, we can equate these two expressions now, and so this will give us this later expression, which involves the magnetic field strength B, the charge on the ions, the radius of the curvature, the mass of the ions, and the accelerating potential. And so the qualities of our ion that really matter is going to be the ion mass and the ion charge. And so rearranging the expression, so we just have the mass and charge on one side of the equation, we get this m over z. This is the kind of characteristic of our ions of interest. And this is equal to this b squared r squared over 2v. So the magnetic field strength B and the accelerating potential V, we can regard these as constants. And so the thing that varies is the radius of curvature. And we can see this on the picture on the screen there. And so we can see that with the heavier ions, so that's a larger m over z, with the heavier ions, therefore we're getting this larger radius of curvature, where it's not deflecting quite so much. And of course the m over z there, our z is typically going to be a 1 plus. So really, if all the ions are 1 plus, all we're really comparing in practice then is the mass, just remembering that it really is mass over charge. So there we go, the heavier ions have a larger radius of curvature. So it's really seeing how the ions emerge from this magnetic analyzer, how we determine their mass when they hit these detectors. Now, that's the kind of classic mass spectrometer. There is a more modern type of mass spectrometer, which we see these days in laboratories, called the so-called time of flight mass spectrometer. And we can see a picture of it here on the screen. And it's actually a much simpler idea. There's nothing magnetic about this one. So again, we start off by creating ions using the similar sort of principle. So we just create the ions, accelerate them by a negative potential, minus v, up to a kinetic energy, half mv squared. And so just like we did before, we can gain an expression for how fast those ions are moving, v. But then rather than send them into a magnetic field and deflect them, all we do is just send them down a straight track. And so they're just going to travel down the track at a constant speed. So yeah, really simple idea. And so obviously they're going to be going at a constant speed. Speed is distance over time. Just make time the subject. So the time it takes them to go down the track is just the distance, which is just the fixed length of the tube, divided by the speed they're going. And then we've already got an expression for speed, so we can substitute that in. We can rearrange that, and we get an expression for m over z. So this is going to involve the accelerating voltage, capital V, which we can just regard as a constant. D, the distance, the length of the tube, again that's just going to be a constant. And so really what it depends on is the time that we measure. So you can see here in this expression that the heavier the mass of the ions, so not surprisingly the slower it will travel, and therefore the longer the time that we measure. It's kind of amazing really that such a very, very simple idea as this actually wasn't how mass spectrometers were originally developed. It's only the more modern, sophisticated ones that use this approach. And I think this is because it's actually a very difficult technical problem to measure these times accurately. And it's only really with sort of modern electronics and technology that we can even measure these times accurately enough for this method to be used. Now, fragmentation of ions. So during the process of ionization, especially using a high energy electron gun, often we do more than just ionize a molecule. We'll often break it up in the process. So it's getting seriously bombarded by these high energy electrons, and often it will shatter the molecule. And in fact there are modern methods these days, so-called softer ionization methods, which are used especially with kind of larger, more fragile biological molecules, because you don't really want them blown to smithereens by the electron gun, especially if you're interested in the molecular mass rather than just the mass of the fragments. And so if a molecule is going to fragment when it's struck by a high energy electron, then actually a chemical bond is going to break, and really there's three ways that it can break. And so we need to really focus on the bonding pair of electrons, which these two dots here are going to represent. And so you see one way that the bond could break, so-called homolytic fission, is when each electron in the pair, as it were, kind of goes back to its original atom. And this will produce free radicals, these atoms with an unpaired electron. So that's certainly one way the bond can break. Or both electrons that are shared in the bond could end up on just one of the atoms. And so that one atom that gains both of the electrons will pick up a negative charge, where it's kind of stolen the other atom's electron, and the other atom ends up with a positive charge, where it's lost its electron. And of course the other way of doing this is that both of the electrons could go in the other direction. So, you know, the A there could end up positive or negative. But either way, ions are being produced with heterolytic fission. And so, interestingly, if we've already got a charge on our molecule, and then it undergoes fission, a bond breaks, we then think about what happens to the original charge on the molecule. So typically, what will happen when a molecule fragments is that that 1+ molecule will produce two fragments, one of which is neutral and one of which is positively charged. There are actually two ways we can generate this. If you look at this sort of eth, what is this? This is the ion of ethane, isn't it, on the bottom left with a positive charge. If that bond were to break homolytically, then it would certainly give those two particles that are shown. Equally, if it were to break heterolytically, if both of the electrons in the bond moved to the right there, that would turn the CH3 plus on the right to a neutral CH3 radical, and it would leave the CH3 on the left positively charged. So actually that bottom left equation, we could get that either from homolytic or heterolytic fission. But what's really quite unlikely was that you get heterolytic fission working in the other direction, whereby the atom that's, as it were, carrying a positive charge to begin with ends up with a doubly positive charge. So this is the very unlikely scenario on the right hand side, which we're much less likely to see. And then the final thing I really need to emphasize here is that the way our mass spectrometer is designed, you're only going to see positive ions, because remember you've got this negative plate, this negative potential, accelerating it into the spectrometer. And so if it's a neutral species, if it's a radical, then it's simply not going to get accelerated by the field, so it won't even enter the spectrometer. And if it were a negatively charged ion, it's going to be repelled by that plate, so again it's not going to be going to the spectrometer. So we'll get a whole range of fragments potentially being produced, but we'll only actually detect those ones that are positive ions. We need to remember that. And so now we've got some exercises on mass spectrometry, get you thinking. So you may want to be stopping the video periodically, having a think about these things. So with our first equation, our first question here, when a unipositive molecular ion is formed, it often decomposes into two species. What charges are they likely to be? So we've just talked about that. Then looking at a specific example, supposing we had a molecular ion of ethanol, it decomposes and a peak m/z equals 17 is visible in the mass spectrum. Can we write an equation? So we need to remember about what makes a peak visible in a spectrum. Then looking on to our third question here, we've got decane, C10H22. So if we regard carbon as mass 12, hydrogen as mass 22, we'd expect decane there to have a mass of 142. It tells us in the question that we actually can observe a peak at 143, one higher than we would have expected, and to suggest which species is responsible. So we need to think about isotopes, and it's told us to neglect any heavy hydrogen isotopes. So it should be pretty obvious really what isotope we're looking at. Then on our next question here, again looking at decane, We also can see peaks at 15, 29 and 43. These are actually very common peaks to see in mass spectra of organic molecules, and so you might be able to work out what those peaks are caused by. And then next up, going to carbon-13, which is very significant in mass spectrometry of organic molecules. 1.1% of carbon atoms are carbon-13. So this explains the 12.01 relative atomic mass of carbon. What percentage of ethane molecules have a mass of 31? So ethane, C2H6, so you'd expect that to have a mass of 30. 31 there is going to be produced by a carbon-13 isotope. And then finally, a slightly harder question, the relative height of the M+1 peak to the M peak. So the M represents the mass of the molecular ion. So M kind of represents molecular ion. M+1, this is where the mass peak comes up one higher. So this will be due to a heavy isotope, increasing the mass by 1. The relative height of the M+1 peak to the M peak in a molecule containing N carbon atoms. And so again, we're only considering carbon as carrying multiple isotopes in this example. And you've got this last question creeping in here. What happens if a molecule gets doubly ionized? So it's not particularly likely, but occasionally high energy electron beam, it might just knock 2 electrons off a molecule to leave it as a 2+ ion. How logically do you think that ought to appear in a mass spectrum? And now here we have some answers. So if we have a 1+ ion that decomposes into 2 species, typically that will be another 1+ ion and a neutral radical. And so looking at the example of ethanol in particular, we've got this ethanol ion on the screen there. And the significant thing is that it's said that a peak of m/z equals 17 is detected. So 17, the only real way we can get 17 is combining an oxygen mass 16 with a hydrogen mass 1. And so if 17 is detected in the spectrum, it has to be in the form of OH+, because only the positive ions are detected, remember. So that means then that when we write the equation, C2H5 is going to have to end up as the radical, the neutral species, and OH is going to have to end up as the 1+ for it to be detected and visible. So next up, we've got this question on decane. So here the decane is appearing in the spectrum 1 greater than its expected molecular ion peak. So that means that one of the 10 carbon atoms has come out as carbon-13 instead of carbon-12. So each carbon atom has got a 1.1% chance of being carbon-13. But of course, in this decane molecule, any one of those 10 carbon atoms might just come out as carbon-13. So the probability that just one of them comes out as carbon-13 is we're going to have to multiply up that 1.1% by the number of carbon atoms involved. So it's here 1.1 n% of the molecular ion signal is going to be the M+1 peak. So now looking at these other peaks we often see, the 15, the 29 and the 43, these are these common fragments that can break off an alkyl chain. So we've got a methyl, an ethyl and a propyl. But again, we've got to remember that if they're getting detected, they've got to be in the form of positive ions. So that's one thing we've got to remember when we're talking about mass spectrometry. When we're talking about these peaks in the spectrum, we've always got to remember to label them as positive. To not label them as positive kind of is to misunderstand what's going on in the spectrometer. And then this next question was about the ethane, and what's the chance of ethane having an M+1 peak. So again, 1.1% chance for each carbon, 2 carbons in ethane. So it's a 2.2% chance of seeing the M+1 peak. And so in our next question here, it was talking about the relative probabilities of the molecular ion peak M and the M+1 peak. So for a molecular ion peak, for n carbons in the molecule, for each of those carbons we've got this high probability of it being carbon 12. So if it's 1.1% chance of being carbon 13, that would leave it as a 98.9% chance of it being carbon 12. There is such a thing as carbon 14, but that's absolutely minuscule in comparison. We needn't worry about it here. And so 0.989, this is this 98.9% chance, raised to the power n. This will be the probability of the m peak coming out, so where each carbon comes out as 12. And so if we want to have an m plus 1 peak, then it means that for one less than n carbons, we're working on this 98.9% probability, 0.989, and then we're multiplying that by the 0.011, this is the 1.1% chance that one of the carbons comes out as carbon 13. But if there are n different carbons in the molecule, there are n different ways, there are n different possibilities for a carbon atom to come out as carbon 13, so we need to multiply it by n. And so then the ratio of these two, we're going to have to take these two expressions, so the n times 0.989 to the n minus 1 multiplied by 0.011. This then is the probability of the n plus 1 peak, and then we divide it by the 0.989 to the power n. That's the probability of the m peak. And as you can see, there's going to be quite a lot of cancellation there. So the 0.989 to the power of n on the denominator, that's all going to get cancelled out apart from just one of those 0.989s by the term on the numerator. So that leaves us with just 0.011n divided by 0.989. And actually that 0.989 on the denominator, it's so close to 1, it's just about 1% off. It's not actually going to change the value of the 0.011. Certainly not the first two significant figures. So basically it's just going to come out as 0.011n. So again, this is the assumption we were working with before. And then just finally, what happens if the ion happens to come out as 2+? Well, of course, the electric charge of the ion is on the denominator of the m over z sort of characteristic that we're measuring. So if you suddenly double the denominator, where z becomes 2 instead of 1, it's going to halve your m over z. And so when that peak comes out in your mass spectrum, it actually looks like it's got half the mass. Of course, the z has been doubled, so it's taken the overall magnitude down to half its size. I'd like to say a few words about isotopic signatures now, and this slightly relates back to when we first looked at relative atomic mass. We met the idea of a mass spectrum there to find the different abundances of isotopes of atoms, which we use to work out the relative atomic mass. And this is just to make the point that certain elements, on account of the different isotopes and their natural abundances, certain elements, when they appear in a molecule, they give it a very characteristic signature. It's kind of screaming out the page that this element is in the molecule. And two of the most well-known examples are up on the screen here, the bromine and the chlorine. So you can see in the case of the bromine, the two isotopes that we see, 79 and 81, are roughly equally abundant. So we get two peaks about the same height. And so if you've got a bromine atom in a molecule, then you see, rather than just seeing one molecular ion peak, you actually see two of them of equal height with a difference of 2 units between them. So that's really indicative that there's a bromine atom in there, most likely. And in the case of the chlorine atom, we've got 35 and 37 chlorine, but this time not equally abundant. We can see on the figure on the bottom right there that the chlorine 35 is pretty close to 3 times the abundance of chlorine 37. It's quite nearly, and it's about a 3-to-1 ratio. And so if you've got a chlorine atom in a molecule, then the molecular ion peak, the main peak, will be relating to when it's chlorine 35, but then there'll be an m plus 2 peak, 2 higher, that relates to when the heavier isotope is there. And if those two peaks have a 3-to-1 ratio, again, that's really indicative that a chlorine atom is present in the molecule. And one thing we can look at with these spectra, just looking at it in slightly more detail, is what happens with the actual molecules, the diatomic molecules, where you have 2 of these atoms involved. And in fact, one quite nice way of looking at this is probability. So firstly, looking at the bromine case at the top, it's a probability of a half that you've got a 79 or an 81 bromine atom. So if you wanted the lightest isotope of bromine, 7979, the probability of that would be a half times a half, which is a quarter. Likewise, the heaviest isotope, half times a half is a quarter. But when it comes to the middle isotope, with a 79 and an 81, this probability actually comes out as a half. And that's because, whereas it might seem to be a half times a half again, because there's two ways you can arrange the atoms. The first one could be 79, or the second one could be 79. Then we need to take that into account by multiplying by 2. And so the relative probabilities are a quarter to a half to a quarter. And so this explains the appearance of the molecular bromine signal, a 1-2-1 triplet, it looks like. So it reflects the probabilities. And slightly more complicated in the chlorine case. So in the diatomic chlorine molecule, again using probabilities, so with a 3-to-1 ratio, that means there's a 3/4 chance it'll be 35, 1/4 chance it'll be 37. So with the lightest chlorine molecule, 35-35, the probability of seeing that would be 3/4 times 3/4, which is 9/16. With the heaviest chlorine molecule, the 37 and 37, the probability of seeing that would be 1/4 times 1/4, which would be 1/16. And so we could, I suppose, say that the medium one, with a 35 and a 37, it's going to be the difference between those other two and 1. So we've had 9/16 and 1/16, so 6/16 ought to be the probability of that intermediate mass one. Or another way of doing it is we can say you've got a 3/4 chance of 35 multiplied by 1/4 for 37, that gives you 3/16, but there's two ways of doing it. So you multiply that by 2, and that's your 6/16. And so again, what we see there, the relative heights of those peaks for the chlorine molecular ion, they are going to be 9 to 6 to 1. And that's so they're proportional to these probabilities, 9/16, 6/16, and 1/16. And just remember, of course, all of these peaks are labelled with a species with a positive charge, because it's always the positive cations that we're measuring in the spectrometer. Right, now, got a much harder mass spec question here. Really tough one, this. And so this is to do with interhalogen compounds. So yeah, halogens can react with other halogens to form these interhalogens. So for example, bromine can react with fluorine to form this BrF3. And BrCl3 is actually quite an interesting problem. It's not a molecule that's actually known, but you know, let's sort of hypothesize that it might get discovered one day and think what Br3 would look like in terms of all its possible masses due to all the isotopes. And so you see bromine and chlorine are both associated with very characteristic isotopic signatures. So bromine has a relative atomic mass of 80, but rather bizarrely, none of its atoms actually have a mass of 80. Half at 79 and half at 81. So its relative atomic mass just represents the average of those two. Chlorine is unusual in the sense that, like on a GCSE periodic table, chlorine comes up as a half integer mass, 35.5. And this reflects the fact that the naturally occurring chlorine isotopes have a 3-to-1 ratio of 35, which is the more abundant mass, and 37, which is the less abundant. 3-to-1 ratio, so 75% chlorine 35, 25% chlorine 37. So it's quite neat really, because these are they're very close to these simple ratios, and it kind of makes the calculation a bit easier to work through if we're dealing with just sort of simple integers all the time. So what would all the different isotopic ratios look like in BrCl3? Or to perhaps put it another way, what would a mass spectrum of BrCl3 look like? Right, well, let's have a look at the answer. And so we need to consider the bromine atoms and chlorine atoms separately, really. And the way I've gone about it here, if we talk about X and Y, for example, as the two chlorine isotopes, we could have X as the more abundant chlorine 35, Y as the less abundant chlorine 37. And since there's a 3-to-1 ratio in their abundance, the way they combine, having 3 of them in the molecule, I've put together with this little expression here, 3x plus y. So this represents the relative probability, as I say, it's 3 times as likely to find an x as a y. And what I've done is I've cubed it, and this so I'm sort of multiplying the probabilities of one chlorine atom by itself to see what it's like for 3. So I've raised it to the power 3, and so these coefficients that we've got here, it's a bit like Pascal's triangle, except one of our variables is multiplied by 3. So if we take 3x plus y and cube it, then what we see on the screen here are the different coefficients in this expression. So what this represents is that the x cubed here, this represents the chance of finding all 3 chlorine atoms in the x state, the chlorine 35, and this comes out as 27, and we'll see what all the other ones are relative to it. X squared y, this represents the chance of 2 of the chlorines being 35 and 1 of them being 37. Likewise, xy squared would be 1 35, 2 37, and y cubed would be all 3 being 37. And so just really by multiplying out that bracket there, we get these relative probabilities, and this is just focusing on the 3 chlorine atoms. So you can see actually that if we add them up, 2 27s, a 9 and a 1, that adds up to 64. So working with sort of 64 units of probability, we can see then actually we've got an equal probability of 3 35s with 2 35s and a 37. Now, once we've worked out what's going on with the chlorines, we then need to combine it with the bromines. And actually what we've just got coming up on the slide here now is just showing how these masses add up. So when we talk about the x cubed relating to 3 35s, it's just making the point here that this is referring to a 105 contribution to the mass from the 3 chlorines. And so now we combine them with the bromine isotopes, and this is a bit more straightforward because of course they're equally probable. So of course the lightest mass you could possibly have with BrCl3 would be combining the lighter bromine isotope with the three chlorine atoms, all of the lightest isotope. And so the probability of this would be 27, so that's like 27 out of 64, I suppose, from the chlorine combinations, and here we're going to multiply that by 1, so we're saying that the 2 bromines are equally likely. But you'll see when we look at the next mass, 186, there's actually 2 ways of doing this. So what we could do is we could substitute one of the chlorine 35s for a chlorine 37. That's what we've done first of all on the left here. So we've got the lighter bromine isotope with 2 lighter chlorine isotopes, plus we've thrown a heavier chlorine isotope in. And so the 2 light plus 1 heavy chlorine isotopes, we found this had a relative probability of 27. So we're going to multiply that by 1 for the bromine 79. But of course the other way of doing it is we could have the heavier bromine isotope, 81, combined with 3 lighter chlorine ones. And so again, the 3 light chlorine ones also had this relative probability of 27, and again multiply that by 1 for the bromine. And so there are 2 possible ways, each of equal probability, that we can get a total mass of 186. So we combine those 2 27s together and we get a 54. Then again, if you go up another 2, again we could do this by adding another heavy chlorine isotope or another heavy, or changing it to the heavier bromine isotope. So likewise, using the different probabilities we've got here, so having 1 light chlorine and 2 heavy, that was a relative probability of 9, multiplied by 1 to give us the 9. And then the other way of doing it was 2 light chlorines and 1 heavy, which had a probability of 27, multiply that by 1 for the bromine. And so when we sum up the 2 probabilities, that gives us a probability of 36. And then up to the next one, where we can have 3 heavy chlorines with a light bromine, or we could have 2 heavy chlorines in there with a heavy bromine. So again, adding up the probabilities, and then just one way of doing it, the heaviest possible way, where we've got the heavy bromine with all the heavy chlorines, and again this just comes out as 1. So 1 was the probability, relative probability of having all the chlorines heavy, 1 for the heavy bromine as well. So remember when we looked at all the different probabilities, relative probabilities for the chlorine atoms, they added up to 64. So actually, if we multiply that by 2 for the two different, adding together the two different bromine probabilities, that doubles it up to 128. And you can see here that if we actually add up all these numbers, 27, 54, 36, 10 and 1, that will actually give us the 128 from adding together all the probabilities. And so that is what the mass spectrum would look like. If you had BrCl3, put it into a mass spectrometer, what you would find is you would find 5 peaks for the molecular ion. And so assuming we're just making these 1+ ions, the m/z values will come out as 184, 86, 88, 90 and 92. And the relative heights of those peaks would be 27 to 54 to 36 to 10 to 1. So it means actually that heaviest peak at 192 would actually be very difficult to observe. So it's just got this relative probability of 1 compared to 128 for the whole molecule. So you would need very little noise in a spectrum like that to see that tiny little 1 at mass 192. So there you go, that's quite a hard example there where we've got to consider the multiple chlorines, each with their 3:1 ratio, and then combining with 2 types of bromine. So there you go, that's about the hardest problem I could think of. Now just a bit I've tagged on to the end here. This is to do with a curious fact that even when you're looking at the individual isotopes now, you're still not really looking at pure integers. So we can understand why a relative atomic mass wouldn't be a pure integer, like chlorine 35.5, because it's just the average of the different isotopes based on the natural abundance. But actually, even at the level of the individual isotopes, we're not looking at integer masses generally either. And in fact, this kind of follows from our definition of relative atomic mass or relative isotopic mass. It's based upon the carbon-12 isotope being exactly 12 by definition. And so, you might think, well, you could have chosen any element you like, they're all going to be equivalent. But actually, the fact that these isotopic masses are not coming out as pure integers does make us wonder why that is the case. Because after all, the number of nucleons involved, protons and neutrons, I mean, these are integer numbers. So why aren't the masses just following those integer numbers? And of course they very nearly do, and it's only really when you can measure them extremely accurately that you can see these small differences and the fact they're not perfect integers. So what's going on here is that it comes down to the nuclear binding energies, those nuclear forces inside the atom that hold the protons and neutrons together, which are incredibly high energy things. So energetic, in fact, that we actually end up using the most famous equation in science, E = mc². So where you have these astronomically large nuclear binding energies involved, we actually find that they start affecting the mass of the nucleus through our E = mc² equation. So we get a kind of mass energy interconversion, which is a bit strange because we think of both mass as being conserved and energy as being conserved. But actually, when it comes to the domain of nuclear physics, which is basically what this is now, actually mass and energy aren't really individually conserved. You actually have to think about conserving mass energy, considering them both together. So actually the different nuclear binding energies that are involved are actually going to modify the masses that we detect. And so, I mean, this is actually very relevant when it comes to looking at nuclear processes, because in a nuclear reaction, if the exact masses are not going to be conserved, and in order to conserve mass energy, we end up converting mass into energy potentially. So our E = mc² equation we might write as E = delta mc². That's probably a better way of writing it actually, where delta m is a very small change in mass that's associated with the reaction, which you multiply by c² to convert it into energy. Of course, c is a big number, the speed of light, 3 × 10⁸, and then you square that, you've got a massive number, so that's 9 × 10⁻16. So you can see that just a very small amount of mass needs to convert to energy to get very large energies. And that's why the sorts of energies that we see in nuclear reactions just dwarf the sorts of energies that we see in chemical reactions. Before we go on to talk about nuclear fission, I was just going to say a word or two about the atomic mass unit, as I kind of alluded to it in the last slide. This idea that carbon-12, the isotope, is defined to have a relative mass of exactly 12. Well, that's 12 in these atomic mass units. Actually, when biologists talk about Daltons as a mass unit, that's actually the same unit as this atomic mass unit. And so when you're referring to the carbon-12 isotope, of course, what you really mean is that collection of 6 protons, 6 neutrons, and 6 electrons that makes up a carbon-12 atom. But we made the point in the last slide that actually not all isotopes have integer masses. So I'm just going to look at this in a little bit more detail. In fact, you can see in this table here, I've looked up the exact masses of these fundamental particles measured in our atomic mass unit. And looking at the numbers in the table there are a couple of surprises I think jump out at us. So perhaps the first surprise is that protons and neutrons don't have exactly the same mass. And of course, before this, we had kind of worked on the assumption that they did. We just were calling them integers. But of course, actually, protons and neutrons are not fundamental particles. They are made up of quarks. So there's 3 quarks in them, and because the quark makeup is a bit different, they actually end up having slightly different masses. So there we go. That's slightly odd. And our second surprise, or perhaps it's not a surprise, having seen the last slide, is that when you take 6 protons, 6 neutrons, and 6 electrons, and add up all their masses, you'd think it would come to 12, exactly 12, because we're defining the carbon-12 isotope as being 12 on the scale. But it doesn't come to 12. You can see it's a bit greater. It's nearly 12.1 actually. We can see on the table. And so we've got a little bit more mass is expected than we actually see. Or to put it another way, a little bit of mass has kind of gone missing. And so this is the mass which is converted into the energy that I referred to last time. So that 0.09893 atomic mass units is actually converted into the energy, and that energy is the nuclear binding energy that holds the nucleus together. So, and because different nuclei have got different nuclear binding energies, then all the actual masses involved are never quite going to line up. None of them quite integers. And so really, just for the sake of a definition, we just say, well, let's just define the scale as carbon-12, the sort of naturally observed carbon-12 isotope. Let's define that to have atomic mass unit equal to 12, and we'll just define everything from there. So I just thought, just finally, looking at atoms, I'll just briefly mention about nuclear fission. So uranium-235, this is sort of the original nuclear fission process. And so the uranium-235 we see in this equation is getting bombarded by a neutron. So it'll temporarily absorb the neutron, turn it to 236, and the 236 splits up, and it forms 2 different nuclei, this barium and the krypton nuclei, and also gives off 3 neutrons. It actually doesn't have to go into barium and krypton. There are other different combinations, and this is just one example. And here's the curious thing, because you see, when we look at the mass numbers in that equation, they do seem to balance. I mean, 235 plus 1 is 236, and if you add up 141, 92, and add 3 onto that, you get 236 as well. So on the face of it, mass seems to be conserved. But you see here on the screen, I've got the absolutely precise masses. So these have been measured in a mass spectrometer. And again, so you can see they're not actually perfect integers. They're very close to being integer masses, but they're just slightly off. And so what we can do is, taking these masses into account, going back to the equation, we can see what the total mass is on each side of the equation. And we see from going from left to right in the equation, there is actually a very small drop in mass. So just 0.18609 of a mass unit. And so this is what might be called a mass defect, where a little bit of mass has gone missing. And so then that mass has to get converted into energy. And so the atomic mass unit, I mean, we sort of use these numbers to count nuclear particles, but to convert it into a proper unit of mass, kilogram, we've got the definition here of the mass unit. So it's this very small number of kilograms, 10 to the minus 27 kilograms. So we multiply that small number by 0.18609, and that will give us the mass defect as an absolute number of kilograms. Then we can finally take that small number of kilograms, multiply it by the speed of light squared, and then there you are. So we get this kind of disappointingly small looking number, 10 to the power minus 11 joules, just when I was saying these forces were astronomical. But of course that is the energy released per atom. But don't forget you've got 10 to the 23 odd atoms in a mole. So once you start scaling this up to the kinds of quantity that we see, in experiments, you are looking then at absolutely gigantic energies. And this really explains why you get these enormous energies out of nuclear fission.